You guys can access the notebook, right?
Yep.
Good.
What exactly is the notebook?
It's on the Piazza post for today.
That's in the bottom.
sure everyone's here for deep learning, right? So I guess just to warm up before we begin, are there any questions so far about anything? Course, material, theory? So far? That's a good question. Do you remember, Tony, how it was done prior? Were quizzes timed? I thought you just had to complete it before
What?
quizzes. Are they, there's no specific
Oh,
time,
there's
right?
no timing for quizzes. You have three times, I guess. So you can do it 3 times, but there will be different questions in the 3 times that you try to do the quizzes. Yeah. So just try to aim for it.
Anytime in the 2 days window.
Right, you just have to do it before the due date, that's all. Anything else?
And it will be the best score of the 3 attempts.
Yeah, that's correct. We'll wait a little bit longer. Kind of convoluted.
One. No, the question was part 1.
Right, so all of the homeworks except 5 are 2 parts. Part 1 is more conceptual and theoretical questions, and part 2 is programming and PyTorch. I believe so, yes, on Saturday, which is a study hall, but we call it hackathons.
You happen to know what time?
I am not sure, I'll have to check the schedule. Did we post a time for that, Tony?
I think we haven't, but we will do it on Piazza.
Wait a few more minutes. Say 8:05, how's that sound?
Sounds good.
Any other questions, guys? Is this This is not really a formal lecture. It's meant to be more open and free form. I would like everyone to just talk if you have questions or want to share ideas. We're all equals here. We're all friends. Anyone want to add anything, ask anything? Ideas, thoughts, concerns? Yeah.
I'm still waiting, so,
Okay.
so when will be latest?
Not sure. It's usually gone in like, what is it, like the first week or so?
First week or second week, but if you're in the wait list, you're guaranteed to end the class, I guess. Yeah.
Yep. So just hold on there. You'll be fine. Anything else? Okay. It's only the first week. I guess I have one. So regarding like teams, I guess you guys have probably started reaching out and trying to form teams and stuff. What ideas do you guys have, or I guess what would be the best way for people to, I guess, come up with ideas for team projects? It could be like through Piazza. I was talking with the IDLTAs about this, how you might want to form a team based on whatever your project idea is. I'm not quite sure how to go about it. Kind of open-ended. Maybe Piazza?
Everyone put in the ideas and something like that.
Sure.
When we have that ready, but we haven't posted it. But later in this week or next week, I guess you'll have a forum to look for things. Yeah.
Whoever is brainstorm together and just bring up solutions.
Sure. I missed part of that question. Could you repeat that?
No, we got under the assumption that the study group itself could be the project group, like we could just brainstorm an idea and come up with something.
I suppose that's interesting.
Yeah, you can do that if you want, or you can just form new groups for your project.
Right.
It's,
Okay.
you know, two different groups.
Your study group need not be your project group necessarily. Okay.
Is there any specific deadline for the project? When we should let you know?
Specific what?
Deadline?
Probably when we post the Piazza post, right? And then you should have a certain amount of time
Yeah,
to form
so
groups there.
yeah, so for more information of the project, you'll have to wait till the end of the, maybe near the end of the semester, because this is some sort of the last homeworks for 1185 class. Yeah.
Forget about it.
Oh, yeah, that's fine, yeah.
Awesome. Thank you. Okay, guys, I guess we'll go ahead and get started as more students trickle in, catch up. Is everyone on the collab notebook? Not able to find it? Okay. So. I guess we'll just start off. We could check your understanding. I kind of want to ask like just some conceptual questions from lecture. I'm not sure who has a really extensive ML background, or if maybe this is your first ML class, but I kind of want to ask the big question: what exactly is machine learning? The big question, I know. Yeah.
Algorithms that improve at whatever task they are designed to do over time.
Sure.
By incorporating more and more data.
Yeah, exactly. That's a good definition. Does anyone have maybe a more, I guess, layman definition? Welcome in, guys. ideas? Anyone want to take a stab at it? You don't have to be correct. Go ahead.
Like an approximation function?
Yeah.
Solve like one problem?
Yeah, that's a great way of thinking about it. So I guess the intuition, which I picked up through my coursework, that kind of made it click for me, listed right here in part one, in intuition and motivation. Machine learning is nothing more than a set of techniques for constructing models to approximate functions we do not know, and these models are themselves functions as well. Does that make sense? Understandable? If not, please let me know. So there's different types of models in ordinary machine learning. Lots have been tried. You may be familiar with, say, linear and logistic regression techniques, support vector machines, decision trees, random forests, naive Bayes classifiers, et cetera, et cetera. These are all different types of models. When we're talking about deep learning, we're specifically talking about deep neural networks. Those are the type, that's the model type we are specifically interested in. The reason for that is because we've noticed deep neural networks, just by their inherent nature, have been able to tackle many tasks that have been infeasible with different model types very recently. With that, I guess we'll talk a little bit about theory and some mathematical foundations. This isn't really meant to be extremely rigorous. We're just hoping it can kind of serve you throughout the semester. You can refer back to this. So we talked about MLPs very briefly in class. I believe that was just the last lecture. So we'll do a Socratic dialogue about it. So what can you guys tell me that you remember from last lecture? Lecture prior to that, so far, the story so far. What's that? But before that, let's start with the basic building blocks. Say a neuron. What can you tell me about that?
Accept some input and based on is activated then some output.
Right? How do we represent that mathematically?
Function and based on inputs and you have threshold function.
Right, right. Specifically, I guess I was trying to get at, we're using linear algebra. That's the primary language of what we're doing here. But good answer, good answer. So that's the, what this basically mentions here. You have your affine combination. Here we're calling it ZI. It's an affine combination of your input A multiplied by your weights matrix for your neurons and offset by some bias. And you pass that into some nonlinear activation function, and that becomes the output, which feeds directly into the next layer of your MLP. Another conceptual question: why is it important that we have that our activation functions be nonlinear? Yeah.
Because then it makes no sense. Like we'll use exactly the same output, so we need some different activation function, so it will map on a particular range of numbers. Because otherwise, if we just like linear output, what we get, the input would be basically the same as output. So we need some kind of transformation.
And what would be a consequence of that if we had just say an identity activation? I don't know if the professor talked about it in class, but it's important to know. You were going to say something?
Well, there was the issue, I remember where you talked about something kind of being unbounded, where it just gets oversaturated, there's no way to tell.
Yeah, that's the Hebbian learning. This is post-that.
I see.
Good memory. Any ideas? Kind of hard to think about it, or I guess come up with the answer if you don't sit down and do the mathematics. So the answer is, if you have nonlinear activation functions, when you do the mathematics, your MLP would just collapse to the equation of a single perceptron. That's pretty funny. So that for that reason, those nonlinear activations are extremely important. They kind of provide the fundamental structure of your neural network. So I guess, did we talk about forward propagation in class yet? I think the professor, like, he gave you the basic idea of it, but I don't think he used the term forward propagation. It's exactly what it sounds like. You just put some input into your MLP and it goes through the network and it generates some output on the first pass. So nothing we're not unfamiliar with yet. Loss functions, I don't think we've talked about those just yet, correct? So loss functions they're basically a way of measuring how different the output from your model is to the target, right? And so there are different types of loss functions. There's mean square error. I think many people are familiar with this, at least conceptually, from, say, vector calculus. It's the norm difference between two vector outputs. Maybe not, maybe so. Another example would be cross entropy loss. And it's sort of like it's similar to measuring differences between vectors, except its elements of operation are on probability distributions instead of vectors. In other words, it's a way of measuring the difference between two probability distributions. This is all functional analysis. If you're not familiar with it, it's not a big deal. But so we use these loss functions to determine the error between the output of our network and what we want it to be generating, and we use that error difference to train the network to make the output better and better. That leads us to our next topic, which I'm almost certain we didn't talk about, which is backpropagation. Yeah, I don't think we talked about this in lecture just yet. Kind of curious how to tackle it. Tony, what do you think?
I think we have it right.
What do you want to say?
Does anyone have any questions for sections 1 to 3? Confused about it, maybe? About the mathematics?
Yeah.
Can you repeat again what you said about the non-linear activation?
So if you have an identity activation function, right, or I guess a linear activation function, if you do the mathematics, doing the forward propagation, what you'll find is that the equation that it outputs is equivalent to a single neuron. So the nonlinear activation functions prevent that issue. So they're crucial to get neural networks to learn anything large or useful.
Yeah, I'll make a note to it. Do you have chalk?
Somewhere.
I need something to write.
Probably note it down digitally.
Okay, so I'll just maybe talk about it. So for neurons, the equation is simple, right? So it's y equals to wx plus b, right? So if you have linear activations, you stack a lot of neurons one before each other. So it's gonna be can I type it?
Yeah.
Okay, so I'm gonna make a new text area. Y equals to wx plus b. So this equation is just for one neuron. So if we stack it up,
Where x is your input.
yeah, x is your input,
Single input.
w is your weights, and b is your bias. So if we have several layers of such neurons, we'll get y equals to maybe w1, and then this is the first layer, w0 times x plus b0 plus b1. So this is the equation for two neurons. For each layer, there's only one neuron. This is the equation, right? So if we simplify it, so this is also the equation for two-layer network with linear activation. Okay, so if we simplify it, you're gonna get w1 w0 times x plus w1 b0 plus b1. So you can see here, this is actually a bias, and this is the new weights. So this is essentially the same as one single neuron. That's the effect of a linear activation. So if we add some nonlinear activations like ReLU and JLU or some function, we can no more simplify it into like those forms. So in that case, your network can model more complicated functions that's not linear functions. So yeah, that's the reason.
Guess we're sans chalk.
You wanna get back?
Yeah, sorry, they were supposed to put something in here, that's not really our thing.
No, okay. Sorry, guys.
Yeah, sorry, I'm not sure.
No worries.
Any more questions? Does that sound clear to you? Yeah, alright.
And so the next step from that is back propagation, which I don't think, that's probably too complicated to go into huge detail here. We'll probably leave it for next lecture.
But maybe talk about what it is.
Right,
Yeah.
so the basic idea of back propagation is exactly what we described. You have the output of your loss function, which tells you the difference or the error between your network's output and what you want it to output. And you use that information to, I guess, tune the weights of each layer going backwards into the model. So it's kind of like reverse engineering the network, if that makes sense. That's a pretty conceptual or high level way of looking at it. And there's an algorithm, all that stuff, it's actually down here, using gradient descent. There's all sorts of different algorithms for training your network, but that's the basic idea. Back propagation is, it's the way of computing the initial gradient that you use to perform gradient descent. It's not the optimization algorithm itself. This will make more sense later after next week, but for right now, just try and hold on to that. Yep, so here's gradient descent, exactly like this. So you're trying to find your weights, right? It's similar to, I think in Calc 1, you guys had to do Newton's method, right? Or you were introduced to it, at least partially. It's the same idea, just extended to higher dimensions for minimizing your loss function. And that's what finds the weights. You're training to find the weights that minimizes the error between the output of your network and the labels or the target of what you want it to output. Training algorithms, different kinds of training algorithms. We're actually going to probably use one here when we get to code. So yeah, more conceptual questions, overfitting and regularization. I think everyone is familiar with, say, overfitting and underfitting, right? From earlier machine learning classes. Can anyone tell me about those? What they mean? Yeah.
Overfitting is when the model learns the training data, so where it basically memorizes it, but it cannot generalize.
Right.
And underfitting is the opposite, where it just doesn't learn enough.
Right. And that leads to, each one of those leads to.
Well, overfitting leads to a very high test error and like a very high training accuracy and a very low test accuracy.
Right.
And underfitting is a low accuracy for training as well.
Right. And so in the, I guess, the machine learning lingo, what would those be called?
Okay, so the overfitting situation gives you high variance.
Right.
And low bias, and underfitting gives you a high bias.
Right. And so in plain English, can you explain kind of what that means individually?
The model, when it's overfit, has learned every single slight difference in the training data.
Mm-hmm.
That's what the variance is. So it's like the curve sticks too perfectly to the training data points. And for underfitting, it's like a very simple model that's not complex enough to model the training data itself.
Right. And so the way I remember it being described to me is when you have a model with high variance, it has it's because it is overfit to the data, it has a lot of complexity in the model. And so, like you said, when you apply the training data to it, it performs extremely well. But when you start giving it arbitrary data, it can either give you very good performance or very poor performance because of that, how chaotic it is. So that's what we mean when we say it has high variance. There's no clear repeatability on novel data that you can observe. And high bias is exactly the opposite. It performs very well around certain data, trading points and testing points with your data, and other points it will simply miss. Correctly?
Sorry, I didn't know.
No worries. With high bias, your model will perform well around certain types of data, but if you venture too far out of that, it will struggle to give you useful information. Kind of a rough way of saying it. Regularization. I don't think we've talked about regularization yet, have we, Tony?
No.
In lecture?
No.
Okay. When is the batch norm discussion?
It's much later. Batch norm is maybe 6th, 7th.
Okay.
Of the lectures.
All right. An overview of that is there are certain instances where when you're training a model, it can give you sort of, I guess, unexpected behavior just due to, I guess you'd call it like numerical issues. Like sometimes you have a repeated application of a small weight might make a value go to 0. And so it might struggle for the network it might struggle for that information to be carried forward through the network. So there are ways of, I guess, kind of like fixing that are still meaningful. Those are what regularization techniques are, and you'll go through a lot of different ones throughout the semester. One of them is batch norm, which is very simple. It's basically if you have a value that is decaying too quickly, you can kind of reset it by just multiplying by its inverse value, and that sort of normalizes it again. Rough way of thinking about it. Bias variance trade-off, that's basically what we talked about. Cross-validation, similar with regards to validation data. Lastly, we have hyperparameter tuning. Tony, did you, this kind of bleeds directly into your code. Did you maybe want to?
Yeah, sure. Maybe I want to demonstrate the TensorFlow playground.
Sure.
So that's a kind of visualization about, playing around neural networks without any coding. So can I?
Yeah. Yeah. So
I'll just use.
Oh, okay. Yeah. Go ahead.
So this is the address of it. How many of you have played around with this? Maybe raise your hand. Yeah. So I think this is a very good tool for beginners to learn about neural networks, like what is it, how increasing depth or decreasing the depth or increasing the width will change the change your network. So for now, it's defaulted to this kind of data. So you can see on the right of the screen. So we want to classify whether the data is blue points, which is class 1, or those yellow points or class 2. So
hello. Could you please share your screen on Zoom, because we can't see what you're showing.
Oh, we didn't share screen.
So.
You guys should be sharing.
Okay.
Is it sharing?
Yeah.
Okay. Can people on Zoom see it?
Yeah.
Okay.
Yeah, all right.
Good. 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 All right, go ahead.
Okay. So starting from the question of linear activations and non-linear activations, I'll start it with linear. So if I try to train this model, start here, see it doesn't converge. Why is that? So we can see that in the last layer, the function it represents is just a straight line. It's still linear, right? So, but what if I change it back to tanh or sigmoid or even ReLU. The last output layer is now representing some nonlinear functions. This is the power of your activation functions. And also let's learn about learning rates. So that's part of your hyperparameter. So that is how fast you want to descend your gradient. So default is 0.03, and let's start it. So let's see, your task loss decrease, it converges like in 300 or 400 epochs. And what if I change it to a smaller value? Like, see, the convergence is much slower. It is not convergent because your learning rate is too small, or it is in the end. Okay, 700, 800, maybe 1,000 more. Yeah. So this is one of the hyperparameter. So, and also you don't know what is the exact number you want, but you have to do a lot of experiments, or we call it ablations, to find it. And so this is the regularization we just talked about, but since we haven't covered it, I'll just skip it. And also we have all sorts of data. You can change the depth of your network. If you want to do it, you can maybe play around it by yourself. But for now, we'll get back to our coding part. So we'll get to some codes of PyTorch. So maybe this is your first time using PyTorch, right? Does anyone have used PyTorch before? Okay, one there. Oh, a lot of you,
Quite a few
right?
people have. It's good.
Yeah, so you might have learned a lot during Recitation 0. Yep. So also we're still using, oh wait, screen's not here. Is the people back in the room? Okay, just a second. So how many of you have heard MNIST, the digit recognition task? Okay, a lot of you, right? How many of you have maybe written some neural networks to do this task? Okay, so the number is decreasing. So we'll use that as an example to maybe, since this is very beginning of semester, it's a really good example to learn about PyTorch pipelines. Okay. So how do we combine all of those stuff in those Recitation 0 to, one notebook from end to end, from data to training and to evaluation. So this is some, we can see that. Okay, so before running this notebook, I want everyone to open this. Maybe if you want to play around by yourself, and also to make things faster, you can change runtime here, change runtime type. So we'll use T4. I'll delete this one. So we'll change it to T4 GPU. That's a GPU of NVIDIA, and so everyone can do it because it is free for every Colab account. I'll save it. And see here, it's allocating, connecting. So it's giving us a new instance of Jupyter Notebooks. So here now we are able to run it. First of all, we are going to install Torch Summary X. That is library to summarizing your network structure. So you will see that later in the course, also later in this notebook, that we will use it really often in our homeworks. Let's install it. Okay, now we're ready to import all of the libraries. Torch Vision, you're familiar with that. NumPy, also familiar. But sklearn, that's for machine learning. But I guess since this course doesn't require machine learning, some of you might have not heard about it. So sklearn, what we are using here is we are just using this matrix. So we want to calculate the accuracy of our model prediction. So we're just using metrics. But anyways, you don't have to learn about this library because a lot of the code about sklearn are written by our starter notebooks. So we have finished that part for you. Just a side note. Also matplotlib, TQDM. So matplotlib is for visualization. So maybe you want to see about the digits. And TQDM is for progress bar. So you can see our training progress. And so this is very important if you are using GPU. We want to.
So you're off the.
Oh, is it back?
It's the HDMI cable.
Yeah, it's not stable, this cable. To touch it, okay. So this is very important if you are using GPUs. So you have to use a variable called device that stores the device you want to use. So here we're using CUDA, so which is the NVIDIA GPU. Does anyone have any questions? The libraries? No? Yeah, that's really simple. Okay, for datasets and data loaders, here we are just using the MNIST dataset from Torch Vision library. So they have everything set up for us. We don't have to, define our own datasets classes. So, but however, in the homeworks, like homework part 2s, you will have to implement your own dataset classes by, inheriting the PyTorch dataset. That could be something else to do it by yourself. But here, to keep it simple, we just, use the existing one. And also for this transformation, that's for transforming the MNIST dataset to tensor. So in this dataset, a lot of data are stored in NumPy, and we want to train the model. And for PyTorch, we're using PyTorch tensors. So this is a transformation that will be applied to every element of this dataset. So we talked about cross-validation, right? So what is cross-validation? That is basically splitting your data into 3 parts, or maybe 2 parts, or maybe several more parts, like 5-fold, 4-fold, but that's not gonna be covered in this lesson. In this lesson, we're just gonna split it into train dataset, test dataset, and validation dataset. And also we want a random split. So we assign 80% of our train dataset from MNIST to our new train dataset, and 20% of our train dataset from MNIST to validation dataset. And also we have a test dataset here.
That's normally what's used in practice as well, is 80-20 splits.
Yep. Also, if you want to know more, you can search online about K-fold. That's a more dedicated way of splitting your data set. So it will give you a better overview, a better evaluation of your model's performance if you use that, but we're not going to use it in this course, so I'll skip it. So let's write some codes here. Oh wait, let me run those cells.
And we do encourage you to explore the PyTorch API because it has a lot of stuff to offer, and the more you know, the better.
Yeah, always refer to the PyTorch documentation. You can learn a lot in there. So see, we have downloaded everything. Okay, so let's create data loaders. Does anyone know which part of the PyTorch we want to use for this? Hence, maybe?
Which object? Which PyTorch object?
It's covering recitation 0. Data loader, yeah. So I'll put a PyTorch document to let you know what it is. So this is the tutorial for datasets and data loaders. It is also very great for you to look at. So there are a lot more detail in this, but we'll skip that. We'll just implement that. Torch the utils. Oh yeah, sure.
Excuse me,
Yes.
can you please turn this on? We are not able to see properly.
The screen.
The screen.
Unable to see
This.
which part of it?
On the TV?
Like here.
On the TV, they can't see it on the
Oh, on the TV?
TV.
Further up.
Top right TV is off.
Oh, okay.
This one?
Correct.
Yeah, I'll wait for that. Is this big enough for you? Yeah? All right. Okay. So we've got some hints here. Data loader. Let's see. So we have to pass in the data set for it. Well, what's the name of it? So the name was train data set. Also, batch size. We'll put it 64 here, but
Tony, HDMIQ.
oh, sorry.
That's what it is.
One second.
Okay. All right, I'll pause there. Maybe you can do some coding on your own. Okay, so it's back. So batch size 64, that might be a little bit too small for T4. You can maybe increase that. It is not always the bigger the better. So it might affect your model's performance, but it might, so I'll just put 64 here. And also we want to shuffle the data set. Does anyone know why we have to shuffle the data set here? So, yeah,
Well, when you're sampling every data set, you don't want to have some sort of order that gives you bias that you're learning.
yeah, that's right. I guess the lecture haven't covered that. So what we always do for training data sets, for training data loaders, we shuffle it. Okay, and also same thing for the validation data set. Same batch size. For here, shuffling is false because we want to, use the same validation loader for all of our epochs, so we have a more consistent result to compare your model's performance between your epochs. Test data set, same thing as validation data set. Whereas, does anyone have any questions? Yeah.
Yeah, so like, how come we don't just shuffle the validation data once and then feed that to like,
Yeah, that's a great question. You want to shuffle the validation data set only once before the training, right? Okay, so this is actually down here. See, we have a random split. So for random split, it chooses the elements inside the data set randomly. So that's a kind of shuffling, right? So we have already done that. Or if you don't do it, it's also fine because you just want to make it consistent between epochs. Okay, then is data visualization to show you the digits. So remember in recitation 0, we said that data sets are also iterators. We can just get to the first training sample from it using a for loop. That's what I like, but you can have other preferences or maybe put the stuff inside the for loop. It depends on you. So let's first get to know about the data. The most important thing is about its shape. So what we have here is, so for each of the sample, it has 3 dimensions. You can see here. Oh, wait. The first dimension is number of channels. Since our written digits are grayscale images, we only have one channel, the grayscale, right? It's not kind of RGB images, it's not other stuff of data, so only one channel. The height and width is 28, so that's simple. Now we want to show it. This is the visualization for digit 9, although it shows yellow on Matplotlib, but it's actually grayscale. And also, we want to use x.numpy. So remember that we have already used the 2-tensor function, right, to transform it into a tensor. But however, our Matplotlib only takes in numpy input, so we want to change it back to numpy. So the reason why we are squeezing it is that we want to get rid of the first channel because this is only a 2D image, right? So if we squeeze it, the shape of x becomes 28 by 28 instead of 1 times 28 by 28. So we're just getting rid of the first dimension. So this is digit 9 right here.
Grayscale, the picture.
Yeah, it is grayscale, but because of some default settings of Matplotlib, it's showing yellow, right?
I think it shows it as a heat map.
Yeah,
So
heat map.
it's grayscale, but it assigns a color based on activation, even though it's only a single value associated with each pixel.
Yeah, the greater the value, the more yellowish the pixel's gonna be on the screen. So yeah, but it's grayscale. Anyone have any questions for this part? Yeah? Yeah, squeeze. Okay. So I'll use more code here. So let's say x the shape is for now 1 by 28 by 28, right? But however, NumPy, the Matplotlib takes in the image. An image is some matrix of 2D matrix, right? So we want to get rid of the first dimension. We don't want the channels. So what we do here is x dot squeeze, and also I want to use dot shape. See, the first dimension is gone. Only 28 by 28.
In other words, it condenses it from a matrix into a vector. So it's proper input for our MLP.
I noticed that you specified the batch size for the train validation and test.
Size here?
Yeah, why do we, like, why is there not like one variable for each of them? Do we usually use different batch sizes at any point?
Can you repeat?
Like, it's the same number for all of them, like,
Yeah.
is that usually common, like, is there? one-
Yeah, you can change it. I mean, for a better intuition, I would say I would use a bigger batch size for validation or test loader because, that's something that you will be covering in the later of the course or maybe not. Because we are not calculating gradients of the network when you're validating or you're testing your network. So it will use less memory of your GPU. So in that case, we can make batch size bigger so that your GPU can maybe do more computation in parallel that will make your training faster, make your evaluation faster, not training. So, but for now, I'm just putting in a 64 here because MNIST is a small data set. So whatever I put it here, doesn't really affect the computation time for this GPU. You have to tune it for your homeworks depending on your network size. You will see it later. Yeah?
Why do we have trouble equals false for validation but trouble equals true for test?
Oh, that's my bad. Sorry. Pause here. Okay, thanks for pointing out. Anything else? Okay, yes, we can go to implementation of our model. So remember that we're going to create a MLP model here. So remember that linear layers is basically a kind of matrix multiplication, right? For each weight, each weight multiplies your each sample, and for batches, it's done in matrix multiplication, right? So does anyone want to guess what our input size to our network is? 28 times 28? That's right, because we want to flatten our image before input it. I'll just use height times width because we flattened it. The hidden size, I will just do a random value. I'll do 1024. Output size, so what is our output size here? 10, yeah, 10, because we have 10 classes. Written digits from 0 to 9, that's 10 digits. So we want to output the logics for all 10 classes. Some of you might not have heard logics yet. So that's basically another kind of probability. Correct me if I'm wrong. So another kind of probability that ranges from negative infinity to the positive infinity. So yeah, that's just a more basic explanation of it, but you will learn more in machine learning course. Yeah.
Why did you make your in size 10? 24?
In size? No, that's our hidden size.
Yeah.
So hidden size is your dimension of your hidden layers. So you can choose what value you want, but however, this changes directly to your model structure and it affects directly to our model performance. So you want to do a lot of experiments to find the right value for your task, for your model. But here we are just using 1024 because we are just doing a demo, okay? So, but feel free to change it. I mean, you can do it right now. So you can play around with it, and see what value works great for you.
We just wanted a model with a lot of capacity, just for demonstration purposes.
Yeah. Yeah.
By layer size, do you mean the number of nodes or?
Yeah, number of neurons. So so for each neuron, there's an input for PyTorch linear layers. That's basically the neurons. They have two parameters. One is the input size, and the other is the output size. So what we are saying for input size is how many features are there in the previous layer. So if say this is our input layer, we have height times width number of features for our input. So this is the input size for our first layer. And for our output size, this actually also means that the output size also means the number of neurons. So because for each neuron, it makes one output, right? Because it's basically a linear combination of all of the inputs, right? So if we are saying that an output size of a neuron, an output size of a layer is 1024, we're saying that there are 1024 neurons in this layer. Yeah?
So isn't it like if we increase the number of neurons in this particular layer, the image here will get more accurate. So, but how do we find the optimal number then?
So you're saying that if we increase the hidden state, you're saying that the model's gonna perform better, right? Like better accuracy? So actually, it is not always the case. If you make the hidden size too big, the model size will be too big, right? So sometimes it will cause overfitting, so which will make your performance worse. Because you only have this amount of data, like this amount of data, but however your model size is huge. It has too many neurons. What else? What are those neurons gonna do, right? They have nothing else to learn except the bias from the data. So they will just catch up the useless noise from the data and then make your model make your model's performance worse. So for the second question about finding an optimal number about it, that requires a lot of experiments. But however you want to stick with maybe 512, maybe 1024, or maybe for some really complicated models, you might want to change it to 64 because otherwise your GPU can't really fit it.
So I guess for a more teleological answer, like Tony said, which is correct, is you run the risk of overfitting. Another risk you run is redundancy. So you might have neurons that are added that actually learn no new information. So they're just, you're wasting valuable resources calculating them for no good reason. And so in practice, the width and the depth of your network are often considered hyperparameters, and it's left up to hyperparameter tuning, which we'll get into later in the course. But yeah. Any other questions, real quick? Okay, go ahead.
Okay, so let's do our linear layers. So torch the n and the sequential. This is a function for for stacking off all your layers. So right. So if I say torch and linear, so this is our first layer, linear layer. So what's the two parameters gonna be? Times width. So that's in size, right? So see. In features, out features. Oh, it's gone. There you go. Right. Okay, so this is our out features. So this is the first input layer. We have our hidden size. I'll just put hidden size here. Remember all those non-linearity stuff? So activation function here. Is this the right thing? Yep. So we are using value activation function here. Or you can maybe do some experiments on your own to maybe try other activations. I'll show you where it is. PyTorch activation. So this is a huge sub-library of all those layers and tools for doing your neural networks. But if you click here, wait. Oh, nonlinear activations. A lot of those. So ReLU is what we use most often, but for some other tasks, JLU also is great, and also Sigmoid. Eng, GLU, and I think softmax is somewhere around here. Where is it?
Softmax would be it's a loss function.
Yeah. Oh no, softmax is also a activation function. Yeah. So it will calculate the probability distribution out of the outputs instead of the logits.
Softmax more used for like convolution.
For what?
Softmax is mostly used for convolution.
You can use it for any networks. MLP, since we are also outputting logits or probabilities for our MNIST tasks, but we are not using it here because the softmax is done in our loss function. We are going to use cross entropy in this example, and the cross entropy in PyTorch implements softmax for you. It uses some sort of log softmax trick, if I remember it correctly. So that's just for numerical stability, and that's something just to mention. And also our final upper layer.
A few more stacks, just for demonstration.
More stacks?
Yeah.
Yeah, that works too. So I'll first do our upper layer, so our size. right? So let's do more layers, make it deeper.
Or we could try the, just the one layer, just
Yeah,
show
one layer.
how it
Yeah, sure.
performs. Then we could add more.
Okay, so we have defined our first model here.
So real quick, how deep is this network? One. Yeah, it's one. It has one hidden layer.
Any questions?
So far, so simple, hopefully.
Yeah, hopefully.
If not, let us know.
Okay, now we are going to initialize our model first. So model 1. Okay, I think I used the same name here. Do I have to initialize it? Okay, so this model 1 here, since we have used sequential layer here, we don't have to initialize it the second time. In most of our cases in our homeworks, we're just defining our own model classes. So that's different from sequential. Then we have to move the model to the device, since we're using GPU here. To move it around, it's really simple in PyTorch, just use model 1.2 device. Then the weights and biases are now stored in GPU. So, yep.
I'm guessing you guys all did the demo in whichever recitation 0 it was that showed you how to use CUDA. Make sure all your tensors are on CUDA, right? Okay. Good.
Okay, and this is the summary here is what I mentioned about Torch Summary X that shows a description of your model, and I will run this. So first, see that we have a summarization of our model here. Shows the number of parameters, total numbers, 814K. And here's a nice table about it, about your layers. The first layer has a kernel of 784 to 1024 because 784 is your input size, height times width, and the 1024 is our hidden size. And this is 10, our output size, number of parameters for each layer. Since this is the activation layer of value, it is just one operation. It doesn't have any parameters that we can learn about it. The ways that we don't have any ways to learn for activation functions. For more clarifications on the summary function, for the summary, see that we have flattened our X, the start name. So first, let's get into our shapes. So for now, our X is shaped like this, right? Still 128, 28. Then what we are trying to do with this flatten here is because we are using linear networks and it only takes in 1D data, right? It applies, repeatedly on 1D arrays. So we want to flatten it so that each neuron of our network will have a global view of all of the pixels in the written digits. Does that sound clear? Right? So by flattening it, it's 784 as the input. So for now, we have defined our network. Any question for this part? Yeah.
What is the move to device? I mean, what are we moving the model to the device?
All of the data you're moving all the data to the GPU, and it tells the Python API to perform all of the calculations on the GPU as opposed to on the CPU.
Yeah, so you have to make sure that all of your data is in the same device. So since we are using GPU for calculations here, we want to move all of our, matrices, the tensors to the same device, which is our T4 GPU here. By moving the model to your GPU, you're basically moving the weights and biases. Those are basically, tensors. We are moving such tensors to our GPU. And also don't forget to move our input data also to GPU. So yeah.
What happens if we don't flatten it?
If we don't flatten it, okay, so I really need to write on the blackboard. But find a great way of demonstrating it.
You don't flatten it.
Yeah,
That even makes sense.
it makes sense, but it's just the wrong different calculation. it actually makes sense because it is also a valid calculation, but this is not what we want. It behaves differently, and I will have to use some sort of graph to teach you how to show how it is now. Maybe I'll just use the text here. So let's say our input is 28 times 28 if we're flattening it, right? So that's 28 times 28. So in this case, what we are seeing in our linear layers is that for each neuron of the linear layers, it applies its weights directly to the last dimension of their input. So if it is 28 by 28, we have a linear layer of input size 28 and input output size of 522. So this means that each neuron has access to 28 features, and we have 512 neurons, right? So what we are doing here is that each neuron, so let's say we only have one neuron. The only neuron does its calculation row after row. So 28 is the height, the second 28 is the row, right? So it does calculation. First, it uses the same weight on the same first row, and then it uses the same weight on the second row, use the same weight on the third row, same weight on the fourth row. Is that what we really want? No, it isn't, because it's using the same weight for all of the rows. But however, in our written digits, not all the rows are the same, right? So we want to flatten it. What we're changing it to is 784. So one array of 784. So one single neuron get access all 784 features and output into, let's keep it constant, 512. So this neuron will have access to all of the rows instead of only one row. It applies different weights to different pixel instead of to different position of the row, different column, right? Yeah, is that clear? If not, I will just draw some.
You didn't say 784, so it works on every single pixel. Right?
Yeah. Okay. Any more questions?
What I miss?
Oh, so just basically seeing.
Oh, flatten.
Flatten, yeah. Okay. Yeah. However, in later courses, you might get to know about convolutional layers. That applies the weights directly on 2D data. So that's much better than linear layers, right? I will not talk too much about it. Yeah?
And you said the weights are applied to individually?
Sorry?
You said the weights are applied to each element individually in that 28 by 28 or each row?
Can you speak louder?
Did you say it's multiplied, the weights are multiplied to each row or to each element specifically?
Okay, for our first example, the weights are applied to each row. For our second example, the weights for one neuron is applied to all of the pixels. So, okay, is that clear?
Yes.
It is? Okay, I'll skip that part. I'll skip the, drawing part. Any more questions? Okay. I'll go to our next part. So we have our model here. We want to also define our training logic. So this is our training logic here. We have a train epoch that takes in the model, the optimizer, the criterion, the data loader. So criterion here is a function for calculating loss. You put in your predicted data and also your true data. So to calculate how far your model output is to the ground truth. So first of all, before training, we want to set the model to training mode. That is because you have some dropout layers or maybe batch normalization layers in your model that haven't been covered, but setting the model to training mode is essential for those layers. To do so, we just have to say model.train. That's really simple in PyTorch. Okay, now this is our training loop. We want to get one loop of our data loader, which is train loader, TQDM here, to show you a progress bar about our progress.
Which trainer are we using?
Trainer?
Yeah.
We're not using trainer.
We're not using trainer.
Just customizing our,
Oh, okay.
yeah, those sort of things I didn't know. So we want to move the data to device. How do we do it again? Data of images and labels, those are two data. How do we move those? Anyone? Yeah, right. Images equals to images the to device. Also, same thing for the labels. Okay, so it's down here. For 4.4 pass, it's also the same. It is simple in PyTorch. We can just do. We have a model here, right? We just have to call model as a function, like a function, not as a function. Model. We want to run forward pass, and our input to model is images. However, notice that images in our data loader is the shape. We have to take care of the shape. So for images labels in string loader. Okay, so let me get the first sample of it. See, for now the images are 64 by 1 by 28 by 28. The leading dimension 64 here is by convention our batch dimension. So there are 64 samples in this tensor. And the one channel, 28 width, 28 height, 28 width. But we want to flatten it, right? So how we flatten it is images the flatten start. Then because we want to get rid of all of those three axes in the end, so I'll just use start m equals to 1. See, 64 times 788, 784. So 64 samples, 784 pixels per sample. That's what we want. Let's just copy paste this.
And remember, start dim being equal to 1 corresponds to the second dimension.
Yeah.
Everything is indexed from 0 in Python.
So we want to flatten everything from the first dimension to the end. That's what we have here. Okay. So we have ran the forward pass. But don't forget to store the results. I'll just call it outputs. Okay. Yeah, that's right. Also, to calculate loss, we are using the criterion. What we are passing in here, let's also refer to any of the loss functions. They share the same signature, I guess. So for value, this is where is it? Okay. M here is an instance of value, and what we want to, oh, that's an activation, sorry. Loss. So we are using cross entropy here. By calling any instance of cross entropy, we want to input, the input is, it's already here, but you can see from the example. Loss is an instance of cross entropy. We're inputting the input and the target. The input here is the output of our network, and the target here is our ground truth label. So, outputs and labels.
So we had mentioned cross entropy earlier in the recitation. Can anyone tell me what it does? What it measures? Yeah, difference between probabilities. Exactly right.
Okay, so that's the end of our loss calculation. We now have a counter of our train loss, so we want to keep track of what's the loss currently in our training progress. The loss item here moves the data from GPU back to CPU and also converts the tensors back to Python integers or Python floats. This is just a tracker. It has nothing to do with the training. And here's the optimizer. We first want a zero grad. So what is zero grad? We might have some gradient information from last step of our network. So we have to zero it here before calculating our new gradients.
Sorry. I wanted to ask, so is it that cross entropy is the default criterion?
It is not a default criteria, but it is a great loss function for a lot of classification tasks.
Okay.
Yeah.
So which loss did we use?
For what?
For the loss equals criterion outputs.
For this, you mean what loss we're using this here?
Yeah.
Oh, we are using cross entropy.
Did we specify that?
Specify, we haven't, we are gonna define it later.
Oh,
Yeah. This is just a function, it's a template function for training logics. And then we calculate our gradient here, loss dot backward. Then we step the optimizer to, you know, to minimize the loss, Here, this is the evaluation loop, but it's almost the same. But be careful that we are using torch.inference mode here, so we want to disable our dropout layers, but that's going to be covered later in this course. And also, we calculate the logics.
Does anyone know what dropout is, just out of curiosity? No, if not, it's not important, we'll talk about it later.
Yeah. Okay, and yeah, I'll skip this part. Okay, so here we're finally defining our own optimizers and criterions, our loss function. So before do that, let's follow the documentation. Are there some of the optimizers you can name? Atom, SGD, yeah, right. So we'll stick to Atom today. That's fine. Atom. Okay, Atom. So this is the documentation for Atom. You can see here there are a lot of hyperparameters that requires tuning. So for each of the homeworks, you have to choose the best value for each of the hyperparameters, right? That leads you to a lot of experiments. But for Atom or Atom W, the suggested learning rate is 0.001. We'll just keep that and leave all of those other hyperparameters to default. I have to put your notebooks here. So, okay, so this is our optimizer. It's now defined. For our criterion, we just mentioned that we are going to use cross entropy loss. Also for cross entropy loss, there's really a lot of more hyperparameters that requires you to tune. So we'll skip that part as well, but you can learn about it in the later of this course or by yourself. And also we're training it for 10 epochs. So I guess we're now ready to train our model. I'll run this. Oh, I haven't defined all params. I forgot to pass in the parameters of the model. So this is actually the reference to all of the weights and biases of the model so that your optimizer can get access to those weights and then optimize it, right? So this is the first parameter. Okay, first define those two functions. Oh. So see, expected all tensors to be on the same device. So what we are seeing here is that some of our matrices, some of our tensors are not on GPU. It might be the weight or it might be the input. So let's take a look. Images, okay. Oh, okay. Typo. This should work. It's training. See? Since the MNIST dataset is really small, it's only gonna take like 10 seconds around that. Our first epoch got an accuracy of 96%, and it will increase. String loss decreases, which means that the model output is less different than your expected output. Okay, the accuracy begins to fluctuate, but I think it's still increasing. Nope. It's only 10 epochs, so it's gonna be like 1 minute. Okay, so this is last epoch. Okay, so in the end, our accuracy is only 97.43. So I believe that if you tune your model better, you tune a better parameters, the validation accuracy can be much better than this. But since we are only demonstrating it, so demonstrating a training loop, I guess this is a great result. The bonus part, actually, you can just skip that part because label smoothing is some tricks for training for cross entropy, and it might not be covered in the course, but you can learn about it by yourself, and it works great on a lot of classification tasks. Yeah.
What is a typical desired accuracy score for like Kaggle competitions and stuff like that?
To what competition?
Kaggle.
Kaggle competitions, desired accuracy.
Yeah.
That depends on different tasks. And depends on the data set. So what I mentioned about I have mentioned about noise, right? For some data sets, and also even for validation data sets, they might have a lot of noise inside. So which means that maybe wrong labels, maybe missing data. In that case, the best accuracy could only be like maybe 80% or maybe 70%. Or there might be other metrics like Levenstein distance, like AUC, stuff like that. So that just depends on tasks you're doing. Yep.
The accuracy started to reduce after some epochs. Is it possible to like change it to the version that has the highest accuracy?
Yeah, it is. That's called the early stopping. But actually you can, so yeah, you're right here. You can see from 97.86 and then it's decreasing, right? And also see the string loss, it decreases to 0.0083 and then it increases to 0.01. This means that the network is converged. You might want to decrease your learning rate because only one drive because you are already at the minimum point of your slope, and then if you want to make it even better, you have to step it. You have to make smaller steps, right? Yeah.
Another thing to bear in mind with that is just because it's performing very well in one epoch and not as well in another doesn't really correspond to that it's decreasing in performance, right? Because it's only looking at that very small subset of data. So it might be, there's different ways of like pooling each epoch results from each epoch, like averaging. Sometimes people take the average of the weights between each epoch to try and get like all of the performance sort of averaged out into a single model. There's different techniques for preserving all of that. But yeah, good question. Someone else? Yeah.
Where?
Could you repeat that? Sorry.
If you see the progress bar, it says 100%, then it says 750 out of 7.
Oh, okay. So this means that there are 750 times 64 samples in our data set. So we're actually performing 750 steps, right? For each step, we're learning 64 samples. That's our batch size. So steps times batch size equals to the total number of images you have in your data set. Yep. Any more questions?
Did we specify the number of steps anyway?
We didn't specify it. It's calculated by the number of elements in your data set. And the elements of our data set is defined here. For division.dataset.mnist is some predefined values from the library.
Okay.
Yeah, because we're just using other people's data set.
I think you could modify that. It's in the Atom setup, right?
Yeah,
You could
yeah.
pass that in as a parameter if you wanted a different value.
These are trainers.
Something like that.
We are not using trainers.
Right.
Yeah.
Yeah.
This data set, the data set you have taken has 28 by 28 pixels, right? For each of the data.
Right.
Suppose I get another data set which has like more pixels. Can I use the existing model to create, or I have to create a new model for that?
You can use your existing models once you adapt your new data to the shape of the old data like MNIST.
So will I have to train it again, or I can just directly test it and?
No, you can't. If you don't, you have to change the shape of your new data, right? If your new data is other shapes like 52 times 52, you might have to resize it to 28 times 28 because.
And then use it in this existing model.
Yeah, but also you have to be sure that it is also handwritten digits. It is also maybe the same style of digits. Also, it is also the grayscale, and it is normalized in the same range as the MNIST data set, so you can use it.
Under data pre-processing and use the
Yeah.
existing model.
Yeah, that's the data pre-processing, or you can train a new model if you want. Yeah.
This is more just a general question, but given, let's say, like a text classification problem where you're given like inputs of different lengths, how do we like make sure that like our input layer can do?
Yeah, that's a
really good question.
That's a really good question. Yeah, we're gonna cover that in the later of the semester, and you are gonna actually learn a lot more about variable sequence tasks like speech recognition. For MLP, what we are keeping constant is that we can also model this using MLP, right? You can use so now we are inputting a 2D array instead of 1D array if you're modeling in your case. So we are modeling each page as a time step, and also for the content of each page as features. So that's 2 dimensions, right? We wanna use the same weights on each page so that the results time steps are the same, while each page is converted to some sort of latent representations. Yeah, and also you have other layers like LSTMs to model those time series stuff. You will learn a lot more about it.
Much thought has been put into answering that question, and many people have come up with some clever solutions, and we'll talk about it later in the course. But yeah, really great question. Anyone else?
So like in class, we talked about the depth of MLPs. It was like kind of as much mechanism for like the efficiency of like how well you could use or how few neurons you could have. So we had talked about increasing the depth of this one. Would we expect to get like higher overall validation accuracy, or just like in say fewer epochs get to the same?
Yeah, all right, thank you. So this is a great question because the number of depth is also kind of hyperparameters you have to tune. You cannot just make it too large or too small to make your performance the best. You have to choose the right value. So if you make your model too deep, there's gonna be problems like diminishing gradients. So which means that some layers are actually calculating nothing. So their weights, their gradient is 0. The model is more learning. So. Yeah.
If you guys need to go, you can go. Class is over. Thank you all for being here. If you have any questions, let us know via Piazza or however you want to get in touch with us.
Like starting with 6 1.